So, welcome back friends. What we realized in the series of lectures in the previous set of lectures was that the methods which we used in trying to use quantum mechanical methods to solve say simple problems in relativistic regime, they completely fail. The moment relativity is introduced, we have particle, antiparticle, multiparticle states. We end up having problems like Klein paradox and also Zitter-Witten-Wiegang and so on. So, now in this regard I would like to mention that we started looking at other kinds of solutions, because we saw that the methods we are using earlier in quantum mechanics, either the matrix mechanics methods or the wave function methods. When I say wave function methods, I mean solving Schrodinger equation in terms of waves, will not work, but we will use part of classical field theory methods, which are essentially things which we know from classical electrodynamics, which are called Green's function methods, but still use wave functions, for this interactions in trying to form the interactions. Okay. Now, the basic idea to jump from wave function to field will come from here essentially. So, that is the reason why I am doing that, but you do not need the full technology of the field theory for this. So, you can do simple tree level computations without knowing full field theory technology, just knowing wave functions, and one more aspect which is two more aspects, which is propagator theory, and second is Feynman Stuckelberg interpretation of antiparticles. So, given these two things and using wave functions, we can actually solve tree level process, and then we do not need to interpret them in full what do you call full technology of field theory. So, we will come to these things one by one. So, what the first step is, of course, to introduce interactions in the sense that we introduce interactions as products of wave functions of different mediators, essentially of different particles. Say for example, the photon, instead of having a potential, an interaction with photon is by using the 4 moment tensor and the vector potential, multiplying the vector potential with the wave functions of the current of the Dirac particle with the wave function of the photon. This is indeed the wave function of the photon, which I will do in a second. Essentially I will tell you that this is indeed the wave function. This should have been covered earlier, but due to the lack of time I could not cover it, but I am guessing that most of you know that this is nothing but the wave function of the photon. Actually you can actually solve this wave equation, and this wave equation leads you to the wave functions of photon. So, what you are doing is just you are multiplying all these things at one space time point, essentially in terms of current interactions. You are saying there is a photon current which is a vector like current a mu, and then there is this current which is psi bar gamma mu psi, which is the Dirac bilinear covariant which current which multiplies this thing. This is how you introduce interactions. So, this is just multiplying this particles, the wave functions of this particle size and A's in at one space time point, and by suitably Lorentz covariant form. Essentially the basic idea is that there should be Lorentz covariant. You cannot multiply a mu with psi bar psi. Okay. The only way you can multiply a mu is with a vector essentially. So, you need to create a vector with the Dirac particles, and that would be only possible by introducing a gamma matrix. So, psi bar gamma mu psi times a mu. So, this is j mu times psi bar gamma. So, this is what we saw last time. Given this, we started looking at propagator theory. Propagator theories are nothing but Green's functions, and we started with a simple example of non-relativistic case. Now, in both the Dirac case and in the Schrodinger equation case, the the non-relativistic reduction of the Klein-Gordon field will always lead you to the Schrodinger equation. In the Dirac case, it gives you Schrodinger equations plus Pauli terms, which are nothing but if you put in an interaction term, essentially it gives you some Pauli terms. Essentially Pauli terms are the spin interaction terms, and that is the one which tells you that the non-relativistic Dirac equation should always carry a spin half particle essentially. Whereas the non-relativistic reduction of a Schrodinger of a Klein-Gordon equation will always give you a Schrodinger equation, okay, without the Pauli terms, okay. Without the Pauli terms, it gives you a Schrodinger equation. Now if you has a Schrodinger equation, so you can use propagator methods even for a Schrodinger in non-relativistic racing. It is a much generic method, and it is as a precursor to how to get this propagator. We started looking at a Schrodinger equation, and then say we started deriving this propagator with the Schrodinger equation. So we started with the Schrodinger wave function, the wave equation at a given time t. This is like we followed the methods of time dependent perturbation theory, and then showed that the Green's function they showed that the Green's function can be expressed in this particular fashion: g of x x prime is equal to g of x x g0, and g0 x x prime in the presence of interaction at a point Vx times g of x x Vx1 x, and so on. So essentially at every point you can put an interaction, and so that is how your Green's function evolves essentially. Now for without interaction, the Green's function is much simpler to evolve essentially, and we also showed that the Schrodinger equation contains since the Schrodinger equation contains a del square operator, and with that you can always show that this where is this show that the Green's function is nothing but a solution of the full differential equation with a delta function source. So that is how did we show that? We showed that the sum of all the solutions of the differential operator is the Green's function. We showed this particular part, we showed this derivation in the last lecture, okay. This is important to know, but the important thing is more is the result essentially. The sum of all the solutions of the differential operator is the Green's function. So the differential operator is the main thing, the Laplacian in this case del square essentially, and the sum of all the solutions of them is nothing but your the Green's function. And using this we can get to the idea that the Green's function is nothing but the solution of the full differential equation with a delta function source. So you can remove the other source terms, just put the source terms to be a delta function, and you get a differential equation, and the Green's function is nothing but the solution of this particular thing, exactly like what I have expressed elsewhere above. Now using this this is a very general statement. This is independent of the equation of motion we are considering. Now the first equation of motion we are considering is essentially the Schrodinger equation, because like I said, both Dirac and what do you call the Klein-Gordon fields reduce into Schrodinger equation. So that is interesting to see what happens. So we start with a delta function source, write the Schrodinger equation with a delta function source, and then so the solution is nothing but your Green's function. And now we see we can express this entire expression in terms of momentum representation. In the momentum space it becomes like this, and low and below, okay, we have the Green's function in the momentum space given by p square minus by 2m omega minus p square by 2m plus I epsilon. There is a reason why I introduced this concept called I epsilon. I will come to that in the next lectures. So I have not told you about I epsilon, but I will tell you about the I epsilon in coming lectures essentially, why it is required. Now a more detailed explanation for why this is called the Feynman prescription, and the Feynman prescription will come in quantum field theory 1 course. But anyway I can use this the same prescription here also without going into the full field theory essentially. In field theory, in quantum field theory, the propagator is meaning its propagator is derived after second quantization. Okay, in quantum field theory the propagator is derived second quantization is nothing but quantization of the fields. Of the fields, it is nothing but quantization of the fields, it is a misnomer. Okay. Second quantization is nothing but quantization of the fields. We will do a part of it in the coming days, but right now why we are interested in Schrodinger propagator is the reason why we are interested in the Schrodinger propagator using different techniques. So we are learning several techniques. Okay, the course of course during the course, if after I finish this course I offer another course on quantum field theory 1, I hope I will cover these aspects also, and then again compare the both approaches essentially. So these approaches are also useful essentially because both are equivalent at the tree level, but higher order becomes complicated essentially. So you need the full field theory thing, but for most of the basic process at tree level you can use this essentially. Now the reason why we did Schrodinger propagator first is because the non-relativistic reduction equation gives you Schrodinger equation. So this is connected to our methodology essentially. So what we are doing right now, essentially we started with the smaller reduction. Okay, now you can ask the question. Okay, so we started with this propagator. You can use the propagator methods even for non-relativistic cases essentially. Anyway, now just to come back to the question of non-relativistic reduction, just one particular point I want to make a side remark, and maybe I will cover it in some of this is something which all of you should know, and if the time permits I will cover it in one of the lectures essentially, because yeah, it depends upon the time I have essentially, how many lectures I have, how much time I have. So just to comment here, so you can ask the question, what happens to the non-relativistic reduction of the Dirac equation? The non-relativistic reduction of the Dirac equation also gives you so if you do a non-relativistic reduction of the Dirac equation, also gives us what does it give you? It gives you Schrodinger equation, agreed, plus Pauli terms. I think I mentioned it when we are doing Dirac equation to show that the spin of the Dirac equation is determined, because in the non-relativist reduction it gives you the Schrodinger equation, which is nothing but for spinless particles. This contains the spin information. So this Pauli terms, which are nothing but your sigma dot b terms, okay, sigma dot b terms appear here in the presence of a magnetic field. Sigma dot p terms will appear in the non-relativist reduction of a Dirac equation. Now for that you need to couple the Dirac equation in an electromagnetic field and then do the non-relativist reduction. There are small component and large component, and then you take it decouples into two component forms, and that is how you get back these Pauli terms essentially. Now I will do it at some point if I have time permits, but you should remember this part, that the non-relativistic reduction of the Dirac equation should also gives you Schrodinger equation plus Pauli terms. Okay, now coming back to the question we have, essentially now let us move to a relativistic example. So the known relativistic example, okay, so we have done a non-relativistic example of the Schrodinger equation, and we have derived its propagator in terms of Green's functions, and we will see some general properties of these propagator theories before proceeding further for the Schrodinger, Klein-Gordon and Dirac propagators. So you see that the propagator of the Schrodinger equation is given by 1 by omega. Omega is nothing but E is equal to h cross omega is the eigenvalue of the energy, okay, it is the eigenvalue of the energy minus p square by 2m. This is obvious because once you do this Feynman then momentum space momentum space decomposition, you see this thing essentially. Now in electrodynamics, so it is relativistic theory. So we use the Green's functions methods for this Poisson equation. So what we have is del square phi of x is equal to minus rho x minus. Okay. Now assume rho is a point charge, essentially a delta function. Okay. Assume rho is of x. So we are starting with simplest examples, essentially it is a delta function localized at x0, okay, localized at x0, and the Fourier component of phi of x decomposition, okay, is equal to d cube of k 2 pi cube phi of k, maybe let me call it as phi tilde of k e power I k x. Okay. I just wrote down in terms of the Fourier decomposition of phi. Now put it back into the equation essentially. So what we are trying to do is equal to we want to say what is what applying, putting it back into the equation, what will happen to this this thing. Now if it act a derivative, because now the delta function rho of x can also be expressed, let me call this as 1 and 2. Now we want to put both of them back into this essentially. So 1 implies, so rho of x integrable d cube of k 2 pi by cube rho p of k e power I k x minus x 0, where rho p of k is nothing but some charge, essentially some charge. So I expressed the delta function also in this particular integral form. There is the integral form of the delta function. Okay, it is localized at some point essentially. So you have rho p of k is nothing but this thing. On the right hand side, on the left hand side I have the del square. The del square I have to operate on equation 2. So 1 implies, now 2 implies k square integral d cube of k 2 pi by whole cube phi of k e power I k x, okay, is equal to integral d cube of k 2 pi whole cube q e power minus I k x 0 x minus x 0. Now you see that I put back 1 and 2 both these expressions into expression. This is the Poisson equation, putting back into 2 1 and 2 in 1 imply, okay, 1 and 2 in 1 imply that this is the thing. Now from this I can get what is phi of k, okay, what I will get phi of k is equal to q e power minus I k x 0 by minus k square. So this is phi of p of k square or q by k square e power minus k x 0. What I had done right now, okay, I have derived what is phi p. I have derived what is phi p in terms of 1 by k square essentially in the momentum space. I have not done. Now given this, I know what is phi p now. Okay, now I know what is phi p or phi tilde of k. Okay, I should not put phi p. I am using notations. I started using it as phi tilde. So this is phi tilde, phi tilde, phi tilde. Now I know what is phi tilde in this relation in 2. With this I can reconstruct what is my phi of x, which is the solution of the Poisson equation. Now this is again an integral which you can solve it. It is nothing by equivalent to q by 4 pi 1 by x minus x 0. Now you have the solution of the Poisson equation, which gives you 1 by r potential, which is very well known, and your Green's function is nothing but 1 by 4 pi x minus x prime, solution of the Poisson equation with a unit charge essentially. Now you can invert this, now for phi tilde of x prime dq of another x prime g of x prime at another point, you can put another row of p and x prime. So you can solve it in various steps essentially, one by one you can solve, adding one more point essentially, one more step and everything. Now this is what all we do in classical electrodynamics. Okay. So what you have is del square g of x prime is equal to minus del cube x prime. So the g, the the Green's function solution, okay, for the Laplacian is with the delta function source function essentially. Now this is the point essentially, this is the point. Now why did we do classical electrodynamics? Now you can also do the same thing starting from F mu nu electromagnetic interaction. You can do the same thing with the electromagnetic interaction. This is nothing but where F mu nu is equal to del mu a nu minus a nu del nu. Okay. So this is now the equations of motion for this box a mu is equal to 0. Now introduce a delta function. And then solve this equation. Okay. Box is nothing but a box I introduced anyway. Essentially here there is no box plus m square is equal to 0. Okay. And this is the source and this is the delta function source. Now this is exactly how we solve for the Laplacian, exactly the same way as you solve for the Laplacian. You solve for the Laplacian, write it in terms of momentum operator, expand, take the Fourier modes of everything a mu Now this we will not call it anymore a mu, we call it as g x prime, okay, because we know that the moment you put in delta function source, this gives me I am going to directly give you the answer. The answer comes out to be g of x prime in momentum space would be, okay, in momentum space omega k would just be eta mu nu by k square, eta mu nu by k square. Now this is the reason is because this is exactly like solving the Laplacian, it is exactly like solving the Laplacian except but you are changing the delta function with another adding a delta function in this also, essentially exactly delta function also adding in the time direction also, okay. It is exactly like solving that, okay. Now so this is nothing but the photon propagator, okay. This is nothing but your photon propagator, okay. So you have first an analogy of known example. I have given you an example of the Poisson equation solving, essentially the same thing I am expanding it in terms of further, you can expand it in the same fashion. Now when you do it in quantum field theory, you see there are a lot of subtleties involved and lot of details involved in this, essentially, but right now we are just going to do it as though that we are brushing aside all those details, okay. We are brushing aside all the details, there are several issues with the gauge and everything. Let us say for the present let us just brush aside everything and just use Green's functions method and then derive the photon propagator. What we have done is derived for the photon propagator. Okay, I will stop here, I will continue in the coming lecture essentially on this, okay.